Alright, in this experiment we're going to do electrophilic aromatic substitution. First we're going to take sulfuric acid and we're going to react that, and it's concentrated sulfuric acid with concentrated nitric acid, and we get the protonation of our nitric acid. So the nitric acid takes a proton from the sulfuric acid. Then you have your bisulfate ion, and then you have your positive oxygen there that has the extra hydrogen on it. Then the electron pair from the negative oxygen on the protonated nitric acid comes in, forms a double bond, and kicks out the water. And then you have your very, very, very strong electrophile. And so then we're going to take our chlorobenzene and react it with this very strong electrophile. Alright, and so the attack, the first attack I'm going to show is the major product, is in the para position. Alright, and so the pi bond of the benzene ring in the para position attacks the positive nitrogen. Electrons go to the more electronegative oxygen, and we have our sigma complex. Alright, and so we have our NO2 group that is in the para position to the chlorine. And then adjacent to that you have your carbocation. Alright, and that is called a sigma complex. This is a non-aromatic compound. And this one has 4 resonance structures. I'm going to show you the 4 resonance structures for this sigma complex. Alright, and so the pi bond can come down and have the positive charge on the carbon with the chlorine. The electron pairs from chlorine can come down and put the positive charge on the chlorine. Now this one is there's always 3 sigma complex resonance structures. This one gives you 4, and this one is 4 because of the electron pairs on the chlorine that can come down and form the double bond. Alright, and this is a very stable cation because all the atoms have an octet. Every carbon has 4 bonds, and the chlorine there has an octet as well. Then the electrons can go up onto the chlorine and put the positive charge again adjacent to the NO2 group. And then your final step is your HSO4 minus pulls off the hydrogen that is on this sp3 carbon and reforms the aromatic system. And so you get your major product. Alright, and so you got your para-nitro-chlorobenzene. Alright, and so we have 2 other positions on the benzene ring, and I will show them as well. Alright, and so we showed the para, now we're going to show the ortho. Alright, and when we do the ortho, we do the same thing. The pi bond attacks the positive nitrogen, electrons go to the more electronegative oxygen, and you have your nitro group in the ortho position to the chlorine. Alright, and then you, in this case, are also going to have 4 resonance structures that you will need to show. Exactly the same 4 resonance structures as you have above, except this time the NO2 group is in the ortho position. Alright, and then your HSO4 minus is going to take the hydrogen that's on the sp3 carbon and reform the benzene ring. And you have your ortho nitrochlorobenzene. Alright, and so these are the major products. So a chlorine on a benzene ring is an ortho para director. And so your ortho para products are your major product. Alright, and so we also have a meta position. And so when we show the mechanism for the meta position, same as above, except now our NO2 group is meta to the chlorine. In this case, your sigma complex only has 3 resonance structures. It does not have the stable resonance structure where all the carbons have 4 bonds and the positive charge is on the chlorine. That one is not possible with the meta substitution. Alright, and so your meta-nitrochlorobenzene is a minor product. All right, so a very, very small amount of this will be found when you do this reaction. All right, so I've started the reaction. It had to be started in the hood, and I am done heating it. All the gases have been released. It is now back out on the lab bench. All right, and so in here we have concentrated nitric acid, concentrated sulfuric acid, and we have our chlorobenzene. So that is what was added. So into that flask I added 7.5 mils of concentrated sulfuric acid, 2.5 mils of concentrated nitric acid, and in the hood I heated up to 70 degrees Celsius. Then I added the chlorobenzene, and then the heat shot way up, and then it's been heating for the last 20 minutes. And so now I'm going to pour that onto the crushed ice that I have in the beaker here. Then we're going to collect our solid, get a mass and a melting point, and we are finished. All right, so let's all right, so here is our reaction, and I'm going to pour it onto the ice, and then you get a white solid. So maybe you saw the white solid form. So once all the ice melts, we will collect it with our suction filtration, get a mass, get a melting point, and then we are done with this lab. All right, we got to make sure that our solid is in there. I might add a little more. Oh, we got some there. This up. I'm going to stir it up with my stirring rod. I want to get my solid to be solid and not an oil. Can't quite tell. It looks a little oily right now. Ice to this, so the ice melted kind of quickly. Because if it's an oil, the oil will go through the filter paper. We do not want that to happen. We want the oil, if it is an oil, to crystallize into solid particles so that it does not go through. So I can't quite tell if it's an oil or very fine particles. Alright, so it's definitely a solid now. It is now on my stirring rod, so that is definitely a solid. If it was an oil, it would just melt right off. So, alright, so that is what we want. We want the solid. We've got the solid, and now we just have to collect it on our suction filtration. Our excess ice. Try not to lose much product by taking out the excess ice. Alright, and that's definitely a solid now. Stuck to the stirring rod. Alright. Alright, we're going to let that dry for a little while. We're going to get the mass and melting point. Alright, I don't think we're going to do the melting point. The melting points of the three products are all very different. Since we're getting the three products, we are just going to get a yield. Since the molar mass of all the products are the same, the yield is going to be of the three things. And if we had our IR going, we could, or GC going, or another way we could see the different percentages of each one of those that we have. But right now we're just going to do a percent yield by getting the mass of our product. So So it's a light yellow solid. All right, and the mass, .84 grams. 0.84 grams is our yield. All right. That is the end of the electrophilic aromatic substitution reaction.